connection, maybe surprising one, between mathematics and, well, environmental science.
Yeah, specifically forest resources technology. It's a great find.
It really is. It shows how something like abstract math connects to the real world, doesn't it?
Exactly. We often think of something like calculus as, well, just theory, equations on a page, but this shows a very practical, hands-on application.
Right. So our mission today is to kind of unpack that. How does a core calculus concept integration actually get used in managing natural resources?
Mm,
And the source material you shared really zeroes in on one specific thing, calculating the cumulative water runoff from a watershed.
precisely. And managing water in forests, that's absolutely fundamental, whether you're thinking about timber harvesting, road building, or even predicting wildfire impacts like post-fire erosion.
Okay, that makes sense. But water flow isn't simple, is it? It's not like
Yeah.
turning on a tap.
Not at all. It's constantly changing. Depends on rainfall, snowmelt, what the soil's like. It fluctuates.
So you might measure the flow rate at one particular moment, cubic feet per second or something, but then 5 minutes later, it's different.
Exactly.
So how do you go from that constantly changing rate, these little snapshots, to figure out the total amount of water that's actually flowed off that land over, say, a whole day or a week?
And that is precisely where integration comes in. It's the tool for the job.
Hmm.
Think about it. If the flow rate was constant, sure, you could just multiply rate by time. Easy. But it's not constant. It's variable.
Right. Simple multiplication just won't cut it. You'd get the wrong number.
You would. Integration is essentially the mathematical way to sum up quantities when the rate at which they accumulate is changing over time.
Ah, okay. So instead of just averaging, which might be inaccurate or, I don't
Mm.
know, guessing, integration lets you add up all those tiny instantaneous rates of flow
Over your chosen time period.
to get the actual total volume, the
Yeah.
cumulative amount.
Yeah, exactly right. If you have a function, maybe from sensor data or weather models like the sources suggest, that describes how that runoff rate changes. Well, you integrate that function over time.
And that gives you the total volume for that period.
Exact cumulative volume.
That feels really powerful because getting that total wrong, I imagine, could cause real problems out in the field.
Oh, absolutely. Huge problem.
Like maybe you build a culvert under a forest road based on a bad estimate.
And the first big storm washes it out. Or you underestimate flood risk downstream from a harvested area. It has real consequences for infrastructure and safety.
Yeah, I can see that.
And the sources really highlight this point using integration to capture that variability accurately. That's key. It moves forest management beyond just using static averages.
It gets closer to the dynamic reality of how water actually moves.
Precisely.
So it's taking this abstract math concept, integration, finding the area under a curve, right, and applying it directly to managing water on the land.
It's a perfect example of calculus having real-world impact in environmental science. It's not just theoretical.
It really makes you think, though. This specific example from your source material shows how crucial understanding rates of change and accumulation is for water management. So it does raise a bigger question. How else could these calculus tools thinking about rates of change help us predict or manage other environmental systems? Maybe things like forest growth, or how pollutants spread, or even soil erosion patterns. What really stands out to you when you see these direct links pop up between pure mathematics and the physical world around us?